Hello everyone, this is Dr. Gallenstein, and today we're going to do some examples of optimization, and we're going to do constrained optimization. All right. So the first thing I want to do today is I want to do some examples of optimization, just so that we are comfortable with doing the algebra and the mathematics of it. And then I would like to do some constrained optimization, which will mostly just be adding some additional mathematics to the otherwise optimization problem. Okay, so let's go ahead and begin by taking a look at some optimization examples. All right, so in the last lecture, we talked about, or I explained kind of the idea behind optimization, the motivation behind optimization, and I gave you some steps. I said find the derivative, set the derivative equal to 0, and then solve for x, and that will give us our x star, our optimal value. All right, so let's do some examples of that. Let's do some examples of doing an optimization. All right, so let's clear this out. All right, so let's do some examples. All right, so let's start with a somewhat straightforward example. Let's say we had a function, and it is the function f of x equals 3 minus x squared. All right, so here's our function. The function is 3 minus x squared. So now let's find x star. X star, this is the value of x at which point f of x reaches its maximum value. All right, so let's find x star. How do we do it? Well, step 1, find the derivative. So step 1, find the derivative. Okay, what's the derivative? We'll take the derivative of 3, that drops out. Take the derivative of negative x squared, that would be minus 2x, right? All right, then the next step will be set the derivative equal to 0. Okay, so let's do that to be negative 2x equals 0. All right, step 3, solve for x. All right, well, let's solve this for x. Algebraically, what do? Well, we divide both sides by negative 2. All right, we do that, and then we have x equals 0, right? Because the negative 2's cancel out. 0 divided by a number is just 0. So we have x equals 0. And there we are. X equals 0 is our optimal level. So here's our x star, x equals 0. So the optimal value of x is 0. The function f of x reaches its maximum when x equals 0. All right, so there's a straightforward example. Let's do another example. All right, let's do a little bit more complicated function. Let's say that we are going to take the max. So I'm going to write it with a different notation this time. I want to maximize the function 2x minus 10x squared. I want to maximize this function. What I mean, and I'm going to write it like this. This is going to be the way that I would express it. I want to maximize this function. That means that I want to find the value of x that gives me the maximum value of this function. And this is how I would write the problem, is I'm going to find the value of x that gives me the maximum of this function. All right, so I'm looking for, so I want x star. Okay, so then let's find that. Let's try to solve for that. All right, so remember, step one, what is the derivative? Let's take the derivative of this. All right, so f prime of x is equal to 2, right? So the derivative of the first term is just 2 minus, right, so this is 20x. All right, step two is we take that derivative, right? We take the derivative and we set it equal to 0. So here that would be 2 minus 20x equals 0. Okay, step three is we solve for x. All right, so let's do that. Let's solve this for x. Let's take the 2 over here, subtract 2 from both sides. So there we go, minus 2. All right, let's divide both sides by negative 20. So divide both sides by negative 20. All right, the negative 20s cancel out, so we'll get x equals, all right, the negatives cancel out. We can cancel a 2 out of this, and we'll get 1/10. All right, so x star is equal to 1/10. All right, so we have just maximized the function. All right, I'll pause for a second, give you the opportunity to write that down. Okay, so it's an example. Let me give you another example. All right, let me make this a little bit harder. Here's our next example. Maximize this function, x and y. All right, this is going to be a function that has 2 variables in it. This is going to be an illustration that's a little bit more difficult, okay, but this is going to be very useful. We're going to maximize a function that has 2 variables, x and y. All right, maximizing a function has 2 variables, x and y. That means we're looking for x star and y star. It means we want the value of both of these variables that give us the maximum of a function. All right, well, let's see what this looks like. I'm going to say 4x, this will be the function, 4xy minus y minus 3x squared. Okay, I want to find the value of x and the value of y that maximize this function. All right, this is going to be more complicated. It's going to be considerably more complicated now that we have 2 variables. All right, so we're getting more serious here. So let's do it. We're going to find x star and y star. Well, how do we do it? How do we do it? Remember, step one is we find the derivatives. What does step one look like when we have more than one variable? Well, it's not too bad. It's just we find the derivative with respect to each. So step one, we're going to find the derivative. The derivative of the function with respect to x, okay, and the derivative of the function with respect to y. We're just going to find both of them, all right? So it's maybe not as intimidating as it sounds. We're going to find both derivatives. So let's find the derivative with respect to x. All right, so here's our first term. I'm going to show some of my work here. Here's our first term. So we take the derivative of this with respect to x. So whenever we take the derivative of a number with respect to, let's say x, when we take the derivative of this term with respect to x, we treat everything else like it's just a number. This can be kind of confusing because there's a y in here, and so we might be tempted to think of y as a variable. But when we're taking the derivative with respect to x, we treat y like a number, not like a variable. Okay, so then what's the derivative of this term? Well, it's just 4y. All right. What is the derivative of negative y with respect to x? Well, you'll notice that there is no x in this term. If there's no x in the term, then the derivative is just 0. All right, so nothing happens there. What about here? Well, there's an x here and there's no y, so this should be pretty straightforward. It'll be minus 6x. Okay, so there we go. That's the derivative. Okay, now let's do it with respect to y. So we're back here again. Take the derivative with respect to y. What do we get? We get 4x. Take the derivative of this with respect to y. We get negative 1. Take the derivative of this term with respect to y. And it's just 0 because there's no y in it. And so here we go. We have our 2 derivatives. We take the derivative with respect to each of the variables. All right, and that's step one. Find f of with respect to x and f with respect to y. All right, step 2, let's see, this is y. Step 2 is we're just gonna set the first order conditions. All right, so that's all we need to do is just set these equal to 0. That's step 2. All right, step 3 is solve for, this time it's not just x, we solve for x and y. So this time we're going to solve for x and y. All right, this is where it gets a little bit more complicated. It's not so simple this time. We have to be sneaky. We have to be tricky to try to solve this out. What we need to do is we need to solve these two equations. We're going to take these two equations, use these two equations, and we're going to use those two to solve for x and y. All right, that is our step 3. So let's do that. We're going to solve that we're going to solve these two equations for x and y. Well, let's think strategically. How can we do that? How can we solve these two equations for x and y? Well, first, let's notice that this second equation doesn't have y in it, and it only has x. That means we can solve this equation for x. That would be a good first step. Let's do that. So we have 4x minus 1 equals 0. Let's solve this for x. Let's add 1 to both sides. 4x equals 1. And then let's divide both sides by 4. We'll get x equals 1/4. All right, so there we go. This is x star. So we're already done with part of it. We found x star. And now we need to find the other one. Well, what do we do with this? This equation here is a little bit more tricky. 4y minus 6x equals 0. This has an x and a y in it. Well, we already know what x star is. So let's do this. Let's solve this function for y. It'll be y as a function of x. Okay, let's solve this for y as a function of x. Then we'll plug x star into it and we'll find y. We'll find y star. All right, let's try that. So let's solve this. First, let's take the negative 6x over to the other side. So we'll have 4y equals 6x. And then let's divide both sides by 4. And we'll get y equals 6 over 4x. All right, so then what we can do is let's take x star and plug it in for x. Okay, let's do that. Sum of y equals 6 over 4. We're going to plug 1/4 in for x. 1/4. Okay, and then let's do our math here. 6 over 4 times 4, that's 16. And if you're sharp, we'll see we can simplify this. Let's divide both of them by 2, the top and the bottom, so that'd be 3/8. All right, so there we go. Now we have y star. All right, so there are our answers. We have x star and we have y star. The optimal value of x is 1/4. The optimal value of y is 3/8. Okay, it becomes a little bit more complicated when we solve it and it has two variables, but this is an important skill to have. Okay, so there we have some examples of doing optimization problems. I'll pause here for a second, let you write this down. Let you write that down, take notes on that. So here's an example of how we solve a complicated maximization problem. All right, I'm going to save this one. Just because this one's a little bit more complicated. All right, optimization example 1. Okay. All right, so there we go. We have our example. All right, so now let's move on to the second part of this lecture. Let's write this in black. constrained optimization. Okay, so in the last lecture, I explained the idea behind optimization. And then in the beginning part of this lecture, I gave some illustrations of some optimization. What I just did are examples of unconstrained optimization. That means I just optimized the function as is. Okay, now I'm going to do constrained optimization. I'm going to do constrained optimization. Well, let's just think, just intuitively, what does that mean, constrained optimization? Well, if we think about this from an economic perspective, you'll remember that I mentioned that we make decisions, people make decisions in the context of scarcity. That means that we make decisions subject to constraints. I can't buy an infinite number of cups of coffee because every cup of coffee costs money, and I only have so much money. So I make decisions subject to constraints. That means if I really want to be able to study economic decision making, I need to be able to maximize a function that has a constraint in it, where the decision making process is constrained by limited resources. Okay, so that's why we need to know how to do this constrained optimization. But today, in this lecture, I'm just going to give an explanation of the math, and then in the future we'll really apply it. All right, so then let's just dive right into what does it look like to a constrained optimization. Well, let's say we want to maximize a function. It means we want to find the value of x that maximizes some function f of x. Okay, but this function has a constraint. That means there are only certain values of x that we can choose. What does that mean? That means we're going to add something to this. We're going to say that we're going to find the value of x that maximizes the function f of x subject to, that means constrained by, some constraint. And this is going to be the constraint. It's subject to the constraint that this value of x must satisfy some other condition that we'll say z equals g of x. That we're going to choose the value of x that maximizes f of x subject to some constraint z equals g of x. All right, so we want to find, so we're going to find, that's awful f, find x star. And x star maximizes f of x, it maximizes f of x while also satisfying this additional condition, while also satisfying that z equals g of x, some other function of x. Okay, so this is constrained optimization. We're adding a constraint. Okay, this is our constraint. Okay, so if without this, it would be an unconstrained optimization. That means we're just choosing the value of x that gives us the highest value of the function f of x. But when it's constrained optimization, we're adding something to it. We're adding a constraint. That means we choose the value of x that gives us the highest value of f of x, while also satisfying this constraint z equals g of x. Okay? Now, how do we do that? Well, we use a method that's called the Lagrange method. All right, so we use a method called the Lagrange method. Let me show you what that is. All right, I'm going to delete all of this. We do this constrained optimization by using the Lagrange method. All right, we're going to use the Lagrange method. Well, let me just get right to the point and show you what it is. What we do is we create a new function. So before we had a function f of x, right? We had a function f of x, and then we had a constraint function, some function that constrained our choices on x, and the constraint was this. All right, let me give some names to these things. This function f of x is called the objective function. Objective function. This is the function that we maximize. We maximize, or it could be minimize in other cases. Minimize, sorry for misspelling, the objective function. Okay. All right, and then this is the constraint. All right, so here's the objective function, here's the constraint. The Lagrange method, what we do in the Lagrange method is that we take the objective function, so we take the objective function, and we take the constraint, and we create a new function. All right, we take them both, and we create a new function. We'll call it the Lagrange function. It's a function of x. All right, and what it's going to be f of x plus, I'm going to use a different color here to emphasize what I'm about to write, lambda. Okay. Let's keep our color coding here. It's going to be f of x, okay, plus lambda times our constraint. So it'd be z minus g of x. All right. This function here is the Lagrangian, okay? And just in case the colors are obnoxious, I'll write it in black. F of x plus lambda times the constraint. Okay, so this was our original objective function. This is our constraint. We take both of them, we create a new function called the Lagrange function, and we will now use this function, this Lagrange function, and we'll maximize that. All right, and using this method is what we're going to do. This will allow us to find the constrained optimization, the constrained maximum point. We are going to be able to find the x star that maximizes f of x, that maxes f of x, subject to the constraint. All right, so this is the Lagrange method. Okay, all right, let's set it up more completely and then see it in action. All right, so make sure you have that written down. I'm going to go ahead and erase it, and then we're going to move on. All right, the Lagrange method. Okay, so what we're going to do is now we're going to rewrite our maximization problem. We're going to maximize, instead of the old objective function with just f of x, now we're going to replace it with a new objective function, L of x. All right, the Lagrange function. So writing this differently, let's write out that Lagrange function. So we're going to choose x that maximizes f of x plus lambda times z minus g of x. This is our new function. We are now going to maximize this. We are going to choose x that maximizes this L of x, all right? And we're going to follow the same procedure as we did before. Step 1, find L prime of x. Step 2, establish the first order condition, L prime of x equals 0. Step 3, solve FOC for x. This will give us x star. All right, so the Lagrange method is basically just creating a new objective function that includes the constraint in it. Now this new objective function has the constraint in it. All right, and so now we're going to maximize this. All right, and that will allow us to do a maximization with a constraint. So now this is a constrained optimization or constrained maximization. All right, so those are the steps. Now let's apply it. Let's do some examples. Okay, just like we did before, let's do some examples. All right, erase all that. Now let's do examples. Okay, so let's say that I want you to maximize, I want you to choose a value of x that maximizes some function f of x, and let me give it to you. Some function f of x, and it's going to be it's going to be, let's start off tricky. We'll get right to it. Natural log of x. All right, so basically f of x is equal to the natural log of x. All right, and it's going to be subject to some constraint. All right, and what is this constraint going to be? How about it's going to be z equals, let's do alpha times x. Okay, so this is going to be our constraint. All right, so we have our function. Our function is natural log of x. Our constraint is going to be z equals alpha x. You'll notice, just to be complete here, we have variables. Variables are x. Parameters are z and alpha. Okay. Well, how do we do this? Actually, I'll still use a different color here. How do we do this? Well, we're going to set up the Lagrangian function. All right. So now, to do a constraint optimization, we need to first set up the Lagrangian function. Before we can do the optimization, we have to set up the Lagrangian function. So let's set it up. What's the Lagrange function? Well, it's f of x, so in this case, natural log of x, plus lambda, all right, times the constraint, z minus alpha x. All right, so there's the Lagrangian. And now what we're going to do is we're going to maximize, we're going to choose the value of x that maximizes the Lagrangian. Okay. Then we follow our steps. Whoops. We follow our steps. We find L prime. We find the first order condition. And we solve. All right, so those are our steps. So let's do that. I'm just going to delete this to give myself some more space here. All right. And so we're going to maximize this. In fact, I might even back up here. No, I'm going to keep this. Okay. So what we're going to do is we're going to maximize the Lagrangian for x. So let's do it. Step one. Step one, find the derivative. Derivative with respect to x. So let's do it. All right, so let's start here. First term. What's the derivative of ln of x? What's the derivative of the natural log of x? Well, if you remember, the derivative of the natural log of a number is 1 over that number. So it's 1 over x. All right. Now let's go to this next term. What's the derivative of this? Well, this might be a little bit more tricky. This might be a little bit more tricky. You can think about this in a couple of different ways, but I'll show you one trick, and then I think you'll get to the point where you can do it in your mind. But let me just do one trick here. I'm going to come off to the side. I'm going to come off to the side and just say that lambda times z minus alpha x is the same thing as lambda z minus lambda alpha x. This might make it a little bit easier to find out what the derivative is. So what's the derivative of lambda z with respect to x? Well, it's just 0 because there's no x in it. What's the derivative of minus lambda alpha x with respect to x? Well, that's pretty easy. It's lambda alpha. So minus lambda alpha. All right. So there we go. We have the derivative with respect to x. But wait. We have an extra step. When we're doing a constraint optimization, we have an extra step. We also need to find the derivative of L with respect to this lambda. I'll talk in a minute. I'll talk a little bit later about what lambda is from an intuitive perspective. Okay, so we have an extra step. We not only need to find the derivative with respect to x, but we also need to find the derivative with respect to lambda. So in fact, I'm even going to go back here and I'm going to correct something I did here. Step one is going to be to find the derivative of L with respect to x and the derivative of L with respect to lambda. All right. So we have the derivative with respect to x, the derivative of L with respect to x. Now let's find the derivative of L with respect to lambda. What's the derivative of this function with respect to lambda? Well, if we look at the first term, there's no lambda, so the derivative of this term with respect to lambda is 0. Is there a lambda in this term? Yes. So what's the derivative of this term with respect to lambda? Well, it's straightforward. It's just z minus alpha x. All right. So that finishes step 1. Step 1, check. All right. Let's do step 2. Step 2, we need the first order conditions. Well, the first order conditions are we just set the derivatives equal to 0. All right. So that's easy. First order condition, step 2, done. Now we need to solve it. So now let's solve it. What color do we want? Let's do dark brown. Okay. Let's solve these two equations for x and for lambda. All right, we're going to solve them for x and lambda. Let me erase this to give ourselves a little more space here. We want to find, we want x star and lambda star. Okay. So let's do it. How are we going to do this? This is, again, more tricky. But it's not too bad once we notice that there's no lambda in this equation. So let's solve this one for x. Z minus alpha x equals 0. So let's solve this. Let's subtract z from both sides. So we'll get minus alpha x equals negative z. All right, and then we can get rid of the negative signs. So just divide both sides by -1, and then we'll divide both sides by alpha, and so we'll get x equals z over alpha. You'll notice this doesn't have a lambda in it, so that means we're done. This is the optimal. So we have our first optimal. We have x star. This is our first optimal. Now, you might pause here for a second and say, how do we know this is the optimal? Well, we know it's an optimal if it's a function only of the parameters. So z and alpha are the parameters. We now have x as a function of the parameters z and alpha. That means we're done. If we've solved for x such that x is a function only of parameters, then we're done. Then we found the optimal. We found x star. Okay. All right, so now that we've done this, let's solve this other one. We have 1 over x minus lambda alpha equals 0. So just like I did in the last example of an unconstrained optimization, let's solve this. Let's solve this for lambda as a function of x. All right, let's do that. So let's take 1 over x to the other side. So 1 over x. Okay. Oh, forgot the negative sign here. All right, and then let's get rid of the negative sign and divide both sides by alpha. We'll get lambda equals 1 over alpha x. All right, now what we're going to do is we're going to take x star and we'll plug it in here, and then that will give us our lambda star. So let's do that. All right, so we have lambda equals 1 over alpha times z divided by alpha. All right, so now we just need to simplify this. Well, you'll notice that these alphas cancel out. That makes this pretty straightforward. We will get 1 divided by z. We can see here that this has no variables in it. It's only parameters, which means we're done. This is lambda star. So now we have our solutions. X star, the optimal x, is z over alpha. The optimal lambda is 1 over z. And there we have it. We have completed our constrained optimization. We've found the optimal values for x and lambda. Oops. Okay, so that's a good example. Let me go ahead and save that. All right. We'll do constrained optimization. Example 1. Okay. It's not like in my name. Constrained optimization. Example 1. There we go. All right, so we'll save that one. And let's delete it. Let's do another example. Let's do another example because these can be kind of tricky. So let's do another example. All right. Let's continue with our let's continue with the natural log. I like that natural log function. So we're going to maximize x. The function is going to be the natural log of x. Okay, and it's going to be subject to a constraint of z equals, and what should this function be? It's going to be x minus 3. Okay, I'm going to use a number instead of a parameter here. Although, I mean, the number in a sense is a parameter. Okay. Or let's do an ambiguous parameter just because that makes it a little more difficult. Let's do x minus capital A. Okay. And, all right, so then we have variables. We have the variable x, and we have parameters of z and capital A. Okay, so here we go. Step 1, we have to set up the Lagrangian. So let's set up the Lagrangian is natural log of x plus lambda times z minus the constraint, so minus x plus a. All right, so let's do our optimization. First, we need to find the derivative of L with respect to x. It'll be 1 over x minus lambda. Okay, and then we take the derivative with respect to lambda, and we get z minus x plus a. All right, then we need to do the first order conditions, so we just set these equal to 0. And then we need to solve these, right, for x and lambda. So let's do that. I'm going to change colors to make this a little bit clearer. So I'll do it over here this time. Z minus x plus a equals 0. Let's solve this for x. Negative x equals negative a minus negative z. Divide through by negative 1. We'll get x equals a plus z. All right. This is a function only of parameters. There's no variables here. And so that's it. So we're done. We found x star. All right. Whoops. All right, now let's solve the other one. We have 1 over x minus lambda equals 0. Solve this one for lambda. So lambda equals 1 over x. Again, we'll plug this in. All right. Let's plug it in, move over here. And we will get lambda equals 1 over a plus z. And actually, we'll notice here that we can't do anything to simplify this, and there are no variables, which means this is the optimal. All right, it's a function only of parameters. So there we go. We have our solution. We have the optimal value of x and the optimal value of lambda. So there we go. We've got another example of a solution. All right. Oops. All right, so we're just going to save that image in case you want to look at it. All right, so there we go. Here's an example. Now let's up the ante. Let's make this a more complicated example. Let's let's up the ante. Let's really make this serious. And this is going to be a better illustration of the types of problems that we're going to run into when we really get serious in the next section. All right, so let's, what we're going to do is we are going to do another constraint optimization. But this time we're going to do a constraint optimization. So let's do example 3. We're going to do a constrained optimization where our function has 2 variables. So let's set it up. Let's say I'm going to maximize. I want to find the value of x and the value of y that maximize this function, the natural log of x times y, subject to the constraint, all right, the constraint that z equals alpha x plus beta y. All right, this is what I want. I want to find, so I want x star and y star, and then later obviously we also are going to want lambda star. Okay, well, so to solve this, what do we do to solve this? Well, again, we set up the Lagrangian. So let's do that. Let's set up the Lagrangian. Now the Lagrangian is going to be a function of x and y. And really, technically, it's also a function of lambda, so let's write that. All right, and so what's it going to be? The natural log of x times y plus lambda times the constraint. Okay. Now, if you're tracking with the math review, you'll notice we can actually simplify this. Let's simplify it. This is the same thing as natural log of x plus the natural log of y plus lambda. All right, so we're just expanding that natural log. Okay. So now we need to take this and maximize it. All right. With that said, I want to create some more space here. So let me go ahead and do some erasing. Okay. Let me do some erasing here. And we're going to set up our new maximization problem. All right, so what we're going to do is we're going to maximize y, x, okay? That maximizes the Lagrange function. Okay, maximizes the Lagrange function. Okay. There we go. All right. So, but we're going to follow the same procedure. We're going to find the derivatives, then we're going to create the first order conditions, and then we're going to solve it out. So, what are our derivatives going to be? Well, let's be systematic. We're going to find the derivative of L with respect to x, the derivative of L with respect to y, and the derivative of L with respect to lambda. All right, so we got to find all 3. All right, so let's do it one by one. Let's do it. I'm going to do it in blue. All right, first one. Derivative of the natural log of x with respect to x, 1 over x. Derivative of the natural log of y with respect to x, 0. Derivative of this term with respect to x, negative lambda alpha. Okay, let's do this one. Derivative of the natural log of x with respect to y, 0. Derivative of the natural log of y with respect to y is 1 over y. The derivative of this term with respect to y, negative lambda beta. And then finally, the derivative of this function with respect to lambda, we'll just jump right to it. It's z minus alpha x minus beta y. All right, we want, now step 2, first order conditions, so we'll just set all of these equal to 0. Step 3, now we need to solve. So step 3, we need to solve this. We need to find x star, y star, and lambda star. All right, and remember, these solutions x star is a function only of parameters. What are the parameters? Z, alpha, beta. So that means we will know we have the solution once we've solved it purely in terms of the parameters. Z, alpha, beta. Lambda star is a function of z, alpha, and beta. All right, so let's do that. And this can be challenging, but let's see if we can figure it out. All right, so what we need to do is we need to solve these three equations. We're going to solve these three equations. All right, we need to solve these three equations for x star, y star, and lambda star. This is going to be tricky. This is going to be tricky, but let's do it. There's a couple different strategies for solving this. I'm just going to jump right in and show you a strategy that I would commonly use in a situation like this. All right. So this is my strat. This is what my strategy is going to be. I'm going to solve this first order condition. I'm going to solve it for lambda. I'm going to take this first order condition. I'm going to solve it for lambda. I'm going to take those values, plug it into here. Actually, correct that. Correct me. I apologize. What I'm going to do, this is going to be my strategy. I'm going to solve this for x. There we go. Solve this for y. Then I'm going to take these two, plug them in. Then once these two are plugged into here, I'm going to solve that for lambda. And then once I have lambda, I will have lambda star, and I'll take lambda star, plug it back in to x and y, and that will give me x star and y star. It looks like I'm a football coach and I've just drawn out a very complicated play. But that's it. This is my constraint optimization playbook. And that's going to be my play. We're going to run this play in order to find x star, y star, and lambda star. All right. Now, with our playbook in place, let's go ahead and do it. All right. Like I said, this isn't easy. So we need to kind of do these examples and get a feel for it, and it'll probably take some practice. All right, but let's get right to it. So strategy, I'm going to solve this for x. All right, so let's start doing that. 1 over x equals lambda times alpha. All right, multiply both sides by x. We'll get 1 equals lambda alpha x. Divide both sides by lambda alpha, and we get x equals 1 over lambda alpha. All right, let's do the same thing here. We've got 1 over y equals lambda beta. Okay, so multiply both sides by y, we'll get 1 equals lambda beta y. Divide both sides by lambda beta, and we will get y equals 1 over lambda beta. Now we're going to take both of those and plug them in here. All right, so let's do that. All right, so let's do that. We're going to have z minus alpha times, what is x? 1 over lambda alpha, all right, minus beta times, what is y? Y is 1 over lambda beta. Okay, all this equals 0. We're going to notice here that the alphas cancel out and the betas cancel out. Okay, so we're going to get z minus 1 over lambda minus 1 over lambda equals 0. We can simplify this. Z minus 2 lambda equals 0. Now let's solve this for lambda. Okay. So we'll have as 2 lambda equals z. Multiply both sides by lambda, we get 2 equals z lambda. Divide both sides by z. Okay, come over here, we'll have lambda. This will be lambda star is 2 divided by z. How do we know it's lambda star? We know it's lambda star because it is a function only of parameters. It's a function only of parameters. That's how we know that it is lambda star. Okay, now what we do, now the next step in our playbook here is we're going to take lambda star and we're going to plug it in to x and y, and that's going to give us x star and y star. All right, I'm running out of space here. I apologize, but let's see if we can do it. Let's see if we can do it. All right, x. Actually, I'm even going to make my pen size smaller to see if I can fit this in. Okay, we have x equals 1 over, plugging lambda in, 2 divided by z times alpha. All right, so let's simplify that. That would be 1 over 2 alpha divided by z. That then equals z over 2 alpha. Z over 2 alpha is a function only of parameters. There are no variables in there. That means that that is x star. So we've solved for x star. All right, sorry again for running out of space here. Let's do the same for y. Y equals 1 over, plugging lambda in, 2 divided by z times beta. That's equal to 1 over 2 beta divided by z, which is equal to z divided by 2 beta. We notice here that this is a function only of parameters, not of variables, so therefore this is y star. Okay, so we have x star equals z over 2 alpha, y star is z over 2 beta. So there are our answers. We have found y star, we have found x star, we've found lambda star. So there we go. We've solved that very complicated constrained optimization problem. All right, I'm going to save this one because this one might be one you want to look at. Okay, so there we go. That is a complicated constrained optimization problem. All right, why don't we do one more example if you're not too tired. We'll do one more example. Just because this is so complicated, I want to make sure that we get it. And also, I'm going to try to do a better job of not using up all of our space, so let's do it here. So again, we're going to do the same thing. We're going to maximize, we're going to try to find the value of y and x for some function. All right, what is this function going to be? I'm going to continue with this natural log function here. Okay, it's going to be of x times y. All right, but this time I'll have a different constraint, subject to a constraint of z equals, what should our constraint be? Let's do 3x plus 4y. All right, now if you're a student, you'll recognize this is pretty much just the same thing where alpha equals 3 and beta equals 4, but we're just going to do it again to get some good practice. Okay, all right, first step, set up the Lagrange. All right, x, y, lambda equals natural log, expand that natural log, z minus 3x minus 4y. Okay, now take the derivative of L with respect to x, the derivative of L with respect to y, the derivative of L with respect to lambda. All right, we should be able to do this quickly. All right, 1 over x minus 3 lambda, 1 over y minus 4 lambda, and z minus 3x minus 4y. All right, we want the first order conditions to set them all equal to 0. All right, let's use our same strategy that we used before. So let's solve this for x. How are we going to do it? We'll do 1 over x equals 3 lambda, which becomes x equals 1 over 3 lambda. Okay, same thing here. 4 lambda. This becomes y equals 1 over 4 lambda. Oops. Okay, so we take those, we plug them in down here. So we'll get z minus 3 times 1 over 3 lambda minus 4 over 1 over 4 lambda. All right, equals 0. 3's cancel out, 4's cancel out. All right, we get z minus 2 lambda equals 0. We solve that for lambda, and we're going to get the same thing as before. Well, we get 2 over z. This is a function only of parameters, so we see that that's final. We have our final answer for lambda. Now we're going to take that and we're going to plug this in over here. So we have x equals 1 over 3 times 2 divided by z. All right, what is this equal to? 1 over 6 over z equals z over 6. All right, this is a function only of parameters, not of variables, so this is x star. So we can write that over here. X star equals z over 6. Okay, so we have our final x. Okay, so then let's do the same over here. Y equals 1 over 4 times lambda, so it's 2 divided by z. What does that equal? 1 over 8 divided by z equals z over 8. This is a function only of parameters, not of variables, so it is the optimal. So we have our final answer, y star equals z divided by 8. Okay, there we go. All right, so there's another quick and dirty example, pretty much the same thing as we did before. All right, so I'll save this one too. I think these constraint optimizations can be challenging, so I'll save these as examples. Okay, well, that completes this lecture. In the next lecture, I will expand on this topic a little bit by showing you what happens when you plug those optimal values back into the objective function. But you'll see that next time.